As always, thank you to my Patreons and all my viewers. Thank you for supporting this YouTube channel. You have all been very generous, and I appreciate your support. So I just pushed up a new tag right here to GitHub. This is March 7th, and what I want to talk about today is a refactoring of the BIOS code, because I am doing some work with the disk drive interface. If we look closely at the status of what I'm editing here, I checked out this branch right here, the JRW NHACP branch, which is the one with the tag on it. If you go to the Z80 Retro website and you click on the software project repo for CPM, which is what we're looking at today. If you go in here and you pull this thing down, there's the branch right there. That's one way you can look at what's happening today. Or you can go over, where is it? There'll be like tags. I think we have to go back to the main page over here. There should be, where's the tags? There's a tags button right here. And you can find the 2023-0701 right there. And there'll be a description in there. It'll say that I did this because what I want to do, this is a shortened version of the text. Yes, I added, I'm refactoring the BIOS disk functions. I added multi-disk support that Trevor Jacobs wrote, and I also replaced some multiply routines that Chuck Todd commented on an earlier commit that I did on this branch. So just so you can follow along and figure out where the heck these versions of the files come from. So if you do that and you click on here, you'll be able to get the, if you just want to grab a download of the tar file, which, or zip file or whatever you want to talk about, you can see what's going on in there. And if you want to look at diffs and all that, if you know how to use Git and diffs and all that, you can follow along more easily, see what's going on, okay? All right, so let's look at the bird's eye view of what I'm doing here. So if you've been following my channel, you know I've been trying to work on this new VDP software so we can play some video games and stuff. And it turns out that the rate at which I write the code and compile and load it and then run it, it's going over and over and over and over again. And I'm getting tired of swapping the SD card back and forth between my desktop machine and the retro board. While that is the very much an authentic historic experience, that is disk swapping, it does bear a little getting used to these days. So it dawned on me, I was watching some of the videos that are going on right now with this Naboo machine, and the way the Naboo works is it doesn't have any disks at all. It has a serial port that's running at about 115, 200 baud, and it just accesses all of its disk data through that serial port. And while that's a little bit slower than the SD driver that we use on the Retro, it's in the order of, give or take, about the same speed. Granted, there's some comments from other people that have been throwing out some notes on how to improve the performance of the SD card driver. And somebody said it could even double it. So I got to look into that. And believe me, I'd be thrilled if that goes faster. And I looked at their code, and absolutely it's applicable. That'll be another video. Let's start with high level of what's going on here towards all this end. I want to have network mounted file systems, and I would like the SD card to run faster. And others are trying to contribute things, like Trevor modified the no cache version of the disk routines to provide support for multiple disks. Now, to be able to integrate all this stuff in, we got to make the BIOS more amenable to contributions from multiple people that want to do different things. Like I want to use a serial protocol to get access to data files, and others will want to use the SD card. And I want to be able to do it all at the same time. That takes a little bit of thinking, and that's what I want to talk about today. So let's start with what happened to the BIOS, all right? So over the months, as you probably know, I've been slowly removing things from here and moving them elsewhere, like the disk I/O routines. If we go to the bottom of this file, This should look familiar. You know, our special stack for BIOS routines that need more memory, and the directory buff for the disk I/O, and so on. And then we're including all the drivers. We talked about this stuff was like a year ago, right? Here's a new one, this callgate file. Okay, so what's in there? Well, what's in there is essentially what's missing from the BIOS. Look what's happening in here. There's no disk routines anymore. Reader, punch, what do we got here? The printer, the console, right? Console status, what's all this stuff? This is like the warm boot routine, okay? And before that's the hard boot, the cold boot routine right there. And there's my jump vector table. That's all that's left now in the main retro.asm BIOS file, right? You'll notice these are blue, these are yellow, because there's no dot in front of these, which means that these are global labels now, and these are, private ones that are only accessible within this file. I've talked about that in the past as well, but just a quick reminder, all right? So all the disk routines come from a different file now, all right? So if you don't find them, they're in here, okay? And you'll notice this file's not all that big, relatively speaking, to the other ones that are in here. So let's look and see what's in here. First of all, notice that I called this thing callgate. What this is going to do is it's going to accept calls from the BIOS, and then it's going to redirect those calls to whichever driver is appropriate based on which drive the BIOS, the BDOS, wants to talk to. And by that I mean like A:, B:, C:, and so on. We should be able to support up to 16 drives all at the same time. Let's do a pretty high-level walkthrough of this, and then we'll come back and look at some of the details. There's a one-time cold boot call that's made to this disk init routine. Each one of the disk drivers may or may not require some sort of initialization to take place before the operating system starts running. This is a pretty messy set of code. Took me a few minutes to debug it. What it's going to do is it's going to go through, and for each disk that's configured below, it's going to call the driver for that disk to initialize whatever's necessary for each one of the drives. Now, in spite of the wording I used earlier, this is specifically going to call once for every single configured disk drive. Okay? Not just once per driver. Okay? So make sure you got that right. So basically what we have here is a loop, and what it's going to do is it's going to walk through a table of pointers, and for each one of the pointers in that table, it's going to load the pointer into the HL register using some screwy logic here. We can walk through this in more detail some other time. I hope it suffices to say that this should work. I've tested it. I load the HL register with a value out of a table, and I call this jump to HL routine down here, which does nothing more than jumps to the address in the HL register pair. When the subroutine returns, it's going to return to the instruction after this call. All right? We don't have a way to call the address in the HL register, so I just call one instruction that says jump there. Okay, so that's what's going on here. And we need to save these other registers because these are like indexes that are going through this table of pointers to the routines that we need to call and initialize, all right? And we use the DJNZ back to the loop here because we're counting the number of elements like in the B register up here. How many vectors do we need to invoke, all right? So that's what this loop is doing here. For each thing that we'll see below, it's going to call, as you'll see, an initialization routine for each one of those things. And each one of those things is going to be one configured disk drive, like a drive letter, A, B, C, and so on. The select disk routine is very different than it used to be. The way we should probably look at the data structures that are used up here, okay, before we talk about the new select disk routine. Because this is going to dispatch the select call to the correct driver, all right? And the way it does that may not be terribly obvious by this code here. There's a lot of commented out debug code in here, because it took me a while to get this to work, all right? So don't get too frustrated if you can't understand it in 5 minutes. It probably took me 2 hours to get this darn thing to work, and as you can see, there's only like 24 instructions in the actual code here, and about 100 lines of code in the debugging. So that's generally a clue there, all right? So this can be a little bit confusing, I think. Let's skip over it with the closing thought that what this thing does is it simply calls the select routine for the appropriate drive when the BIOS calls this function here, all right? The rest of these are pretty much much easier. The usual home and set track, set sector, every single one of these does absolutely nothing other than store the sector in the sector variable, store the DMA address in the DMA variable. A lot like what it did all along in the BIOS. Before, we're not going to do any sector translation. If we need sector translation in the future, I'll rewrite this to dispatch the sector translation logic into the appropriate driver subroutine. For now, we just assume everything's one-to-one. The read and the write routines also will simply dispatch the call, relay it to the appropriate driver. And as we'll see in a minute, what happens for the read and write routines, these go get the value of a pointer each time we select a new disk. So up here, when we look at the cell disk routine, and we go through this in detail, what happens is, one of the things it does is it figures out which one of the drivers is supposed to be used, and it goes and finds the actual address for the read and the write function. And in here somewhere, we'll see it poke it into this disk read and disk write routine pointers. So there'll be some variables down there in the bottom of the file that are used solely to hold the address of these two functions in the actual driver. So in C++, this would be a vtable type of thing. This is an abstract class kind of a thing. All right. So what does that mean? Well, what that means is when you call the write routine, when the BIOS wants to do the writing, we're going to go and find the pointer to the correct one. And then we're going to ask if it's 0, then we don't have a drive with that letter. So this is how we're handling the errors. All right? If you go to drive, J, if you didn't configure that many drives, there won't be a pointer, and you'll see above, when you look at the code in detail, it'll set this write routine to 0, so that it'll not have one. It'll go down here. It'll flag the error. We went over this long ago. The return values from the write and the read routines. If there's a 1 in the accumulator, then it's an error. Okay? So if there is no handler for it, it's an error. If there is a handler for it, just like above, we just jump there. Because remember, the BDOS calls the write routine in the BIOS. And in there, it just jumps to here. Well, this one's just going to jump to the current driver's write routine. And when that routine returns, it'll go back to the BDOS, right? This is called a tail call. I think I talked about this before. All right, so the read routine is going to do the exact same thing. Grab the pointer to the read routine. If it's not there, fail. If it is there, it's just going to go down there and execute the correct read routine for the driver. All right, and here's the usual disk dump routine. We've seen this before. These are all global labels, so that in all the drivers for all the different kind of disks can call this. So we don't have to replicate all this code all over the place. All right. These are the things that used to be in the regular BIOS source code in the retro.asm file. This here is new. And what this is it is a pointer to the DPH for the currently selected disk. All right, we talked about this a while ago when we were building the original file system for the retro. When we only had one disk, there was only one DPH for the one disk. We never had to remember where it's at. We never really had to remember even what disk we were using. okay, because it was only one, and there was only one valid, and if it wasn't the one, it was an error, okay? So now we got a little bit more going on. We got to keep track of a few more things, and one of the techniques that I'm using to figure out which driver is supposed to be used for each disk involves this DPH pointer. Well, a lot of CP/M versions don't work this way at all right? So this is kind of unique, at least to the Retro. There may be other ones that do this, but all the documentation talks about building these tables of DPH objects, but that won't work for us. And the reason it won't work for us is because if we do it that way, it will be more difficult to configure the BIOS and for people to contribute more code. It'll require us to hack up too many files, and there'll always be merge problems, and which one do I have and how do I redo this? I'm trying to minimize that kind of headache, all right? So to solve it, I decided to keep track of the DPH that's currently in use. And this is how the drivers and the this version of the BIOS will discern one disk versus another, okay? Almost never will the code we're going to look at even use this, okay? It can, but it turns out that as this thing is evolving, this becomes less and less useful to the drivers in the BIOS, okay? So it's all about which DPA represents the currently selected disk. That's what this new variable down here is going to be. And here are the two variables I mentioned earlier. Here's the current pointer to the disk read routine that's supposed to be used for the currently selected disk, and here's the one for the write routine, the currently selected disk. And these combined represent the drive and the driver that we're supposed to use for whatever disk was selected for the last time that the cell disk routine was called. And you saw a lot of code in there that I glossed over. You can pick through it in detail on your own, but the goal of that code is to get the correct values stored in these three variables so that the read and write routines later on can be found and executed. All right. Down below this, what we do is we need to include whatever drivers we want to use for our particular configuration. Now, this is pretty messy, and I might end up having to record a whole video on just how to do this alone, okay? For now, let's suffice it to say that for each drive that you want to configure, and the only thing, it turns out all these are currently supported. If you want to munch through the code and figure it out, knock it yourself out, have fun, be my guest. However, in order to be backward compatible with where everyone has been for the last year on the Retro, this exact configuration should do. And if we look closely at what this is doing, what we've got is we've configured 4 drives. And all these other ones are commented out, not playing around for testing and stuff like that. Read and heed these comments if you want to play around with these. In other words, if you're going to use the cache, remember, as I said when we were talking about the cache, this cache does not support multiple drives. So if you want to use this one, it can only be for drive 0, all right, which would be drive A, possibly, all right? I'll leave that as a task for the viewer for now. We'll come back to this later. These 4 configurations right here represent 4 drive images on the SD card. The first one starting at 0800, and we've seen this before. We've seen this for a year. That's where the one and only one disk image is that's been on the Retro since the day I started this project, okay? The second disk image is right after that. This is 8 megabytes later on the SD card, right? So we created one partition, as you might recall, on our SD card using the instructions that I outlined early on, which was way bigger than we needed for 8 megs in one of our drives, okay? So it turns out all these logical drive images are all in the first partition of the SD card. And these are currently hard-coded. They're still hard-coded relative to the beginning of the SD card. Eventually, I want to make it so that these are relative to the beginning of the partition on the SD card. But in order to do that, we need to do some more work with the boot code so that it can tell the BIOS which partition it booted it from. Otherwise, the BIOS has no idea how to get that information. If you look closely at any operating system, there's a very tricky little handoff that takes place during the booting between the bootloader and the main operating system startup logic to hand over knowledge like this. And it's a whole nother project in its own self. I'll go to a video on that when the time comes. Meanwhile, we'll stick with these hard-coded absolute offsets for now. Okay? So what am I doing here? I'm invoking this macro called no cache DPH. And we'll see in a minute, this creates a DPH and the associated ALV that goes along with it. And it configures it so that it knows, it being the driver, the no cache driver, can know where the disk image is on our SD card using these addresses here. This is really supposed to be a 32-bit value, but the assembler doesn't know how to deal with 32-bit values, so we put a 16-bit followed by another 16-bit like this. So this is 0000 0800. And this one's all zeros followed by 4800 and 8800 and C8. You'll see each one of these is 4,000 in hex, which is 8 megabytes when measured in half-kilo blocks. All right? We've talked at great length about that in the past. So what this is doing here is it's creating 4 DPHs, and it's creating a private label on each one of them, DPH 0, 1, 2, and 3. Okay? Down here, there's the DPH VEC label that we saw earlier. We'll scroll back up and look at it in a second. That was used by the init code. And the VEC num was the value put in the B register for that DJNZ loop that we saw earlier up there as well. So what this is going to do is it's going to go through these, however many you put in here. There's 4 drives configured right now. The init code will go through each one of these, 1, 2, 3, 4, like this. And it will invoke the init function for each one of those drives in the appropriate driver. And it figures it out by getting those address values out of the DPHs that you've configured and labeled up here. All right? Now, to keep it simple, I only use the no cache for this first version. Let's look at the no cache file here. Now, this is the exact same code that's been in here all along, except for 2 changes. The first change is down at the bottom of the file here, where we're going to see a macro instead of the actual DPH and the ALV that we used to see in the BIOS itself, right? The retro.asm file near the end used to have this big block. I have a whole video where I explain how all these values work and how CPM wants us to configure it and all the values that go into this DPH, okay? Now, what I did is you look closely, there's the official DPH as defined by CPM. I added 2 extra fields after it down here. This is SD block low and high. Now, what this is because remember, we're little endian. So the low byte in a 4-byte address will be at the lesser address. And the most significant byte of the address comes later. So we have 2. These are where those 2 hex values, the pair of 16-bit hex values come from in the macro invocation we were just looking at a minute ago. So the way this macro is defined is it has 2 parameters. And normally every assembler on Earth has commas between their parameters. This one does not, for whatever reason, I do not know. That's a subject for somebody else. Took me a while to figure this out. I think it's an official bug, but it works like this. Let's just live with it, okay? So what does this macro expand to? You'll notice in the other file that we were just looking at, right, the bottom of the call gate file, there's a no-cast DPH macro that's expanded 4 times. So each time you saw it in there, this macro expands and creates all the code here once for each time you saw that macro over there. I mean, that's how macros work, okay? We saw that when we were doing the SD card, or more accurately, maybe the SPI driver with a macro that I used to read 1 bit at a time, all right? Now, a DPH, we don't use almost any of the fields in here. They're all nulled out, or they're scratch pad used for the BDOS or whatever. But the 2 things or the 3 things that the BDOS must have is a pointer to the dir buff buffer, which is shared by all drives, and that's still in the main Retro BIOS source file, so that it can be shared by all the drivers, and we don't want to create multiple ones for no reason, wasting memory, right? And it needs to know the DPB pointer for this particular drive, and that's the thing down here that had all the sectors per track and the extent masks and all that other fun stuff, okay? Whole video on that that we talked about like about a year ago. Okay, so it needs to know where that is. How is the disk formatted? How big are the blocks? How big are the directory entries? Are there reserved tracks? That's the stuff that comes out of the DPB, all right? And it turns out that the same DPB is used for each one of the disk images that are supported by the no cache driver. All right, so all the disks in the no cache driver have the same, what I like to call the same geometry, and that is the values in its DPB, which are all the math up here. Okay, so what happens is when this macro expands, I get 4 copies of this, but in each one of those copies, all 4 of them point to the exact same dir buff. All 4 of them point to the exact same DPB, okay, which is this down here, this label right here. So they're all sharing this. We don't waste extra memory, okay? Each one of the 4 has its own private ALV because you put a dot in front of a label inside of a macro, as I talked about before with the SPI driver. That label is private to the invocation or the expansion, we could say, of this macro. So each one of them has their own separate private ALV, which is defined down here. Okay? Now, this is pretty big. This is a lot of memory wasted down here. This divided by 8, that's a half a K for each one of these. So if we had 16 of these, we'd have 8K of memory in use just by this. We don't have enough room as, configured in the current BIOS and CPM memory sizes and all that. I mean, we could put more stuff in there, move things around, shrink down the TPA and make room for it. Yes, we can do that. Or what we can do is come back up here and we can rethink all this geometry up here. And then the short of it is, if you look at the allocation vector size that I used in this original design, and I should have mentioned it when we talked about it, I'm sure I did, I chose that the 2K, 2048, would be the allocation size, okay? What that means is anything anywhere on the disk would be allocated in 2K byte chunks. So one of the implications of this is that any file that's created must be or consume at least 2K of the disk. Back in the days when you only had 80K on a single-sided, single-density 5 1/4 inch floppy, you did not want this number to be very big because you didn't want to waste all that extra space. You create a little README file that says hello, and that's all that's in the file. You still consume all 2K. That was, you didn't want these to be big. Today, we got 8 megabyte files, and we can have 16 of them, 8 megabyte disks, I meant, and we can have 16 of those. I mean, no one on earth had that much storage back in the day. So creating a 16K byte allocation block would have been ludicrous back in those days. Keep in mind, 80K was the whole disk. So if you made your block size that big, yeah, that would be a problem. All right, you wouldn't want to do that. Today, this might be useful. Now, why would you want to do that over 2K? From what I just said, aren't we just wasting space? Well, yeah, we have plenty to waste. And you know what else it does? Look at all the math up in here. When you have 2K for the allocation block size, this math here is what dictates the number here, and this is my point, that dictates how big this ALV is. And the short of it is, if you got 8 megs, and you divide that by 2K, you end up with this many allocation blocks. Okay? So that's a lot of blocks. And for each block, it has to keep track of what's going on, whether it's in use or not. And that's what the ALV is for. If we make this bigger, like 8K or 16K, this number gets much smaller. Right? I mean, if we make it 16K, this will be 1/8 of the size it is now. And if we do that, this table shrinks way down. So if you want to play around with this, you might want to reconsider how the disk file system is set up. And I'll probably do that at some point. I originally chose 2K because 2K matches, as we'll see in some future discussion, the size of the largest block that you can put in a directory entry in the file system, such that each directory entry in a file that consumes more than one of the directory entries, what are called an extent, or is it extent? I don't know. I always said extent. The point is that if you use 2K, then one extent matches some math and makes it very easy to understand how the directory entries work in the file system and stuff like that. So I chose it so I could record that video without getting too ugly about it, right? Once you go over 2K, then the directory entries become more complicated. Now, the good news is, if you don't care, then don't bother watching that particular video if and when I ever get around to recording it. And the reason is because the directory entries are usually, 99% of the time, entirely managed within the BIOS anyway. Normally, you can ignore all of that when you're writing applications and stuff like that, and it will just work. However, if you care about how it works, it can be somewhat non-intuitive and difficult to understand if you choose a large number in here. And the reason that's true is because there's no good doc that explains what happens when you have numbers like this. You have to just figure it out. And I'll talk about that in the future. But right now, we're at 2K, all right? The result is this is pretty big, and this is why you can't just put 16 of these in the BIOS right now, because they'll run out of memory, all right? So that's what that whole tangent was about. Be careful when you're playing around in here if you're going to use the 2K size. If you want some numbers on how to do the 16K, I'll show you that in a minute. And then you can flip over to that on your own if you really want to, and you create all the drives you want, because you'll be able to fit 16 of these in here easily if your allocation size is 16K. All right. So what else is going on? These extensions down here are where the, like I said, these represent the absolute address on the SD card of where the disk image begins. And we just simply use these as an offset. The original code in the reading and the write routines, as you may remember, there was a hard-coded 800 in hex value. And now that's not true anymore. That hard-coded value went away, and we reach over into the DPH and grab these, and we use this for the beginning block number on the disk. This is the number one reason why we now have support for more than one drive in this particular driver. Okay? So what's going down here with the DPB? No changes whatsoever at all down here. I just simply moved it into this file so that it can go along with the driver that actually cares about these settings. The driver has to go along with these same values in order for things to come out right. But I've added these up here. Look what's going on. Here's the label for the DPB, and the DPB is formally this. Now, in order to make this configurable and not create a big mess for everybody to have to figure out and rewrite everything, recompile it, and set all this stuff, I wanted to find a way, and this, I believe, is one way to do this, such that all you needed to do is list the drives like we just saw in the Colgate file down here at the bottom. I wanted to be able to just say, look, I want to know cache, and I want to use the SD card starting here. That's a definition of a drive. I want another one that starts at some other offset, and so on. Then you put these labels here, over here in this table down here. So this is a table of pointers, and each one of the pointers in here points to these labels here, right? So this is the label that's on the code that comes from that macro, which is a DPH that we were just looking at. And then inside this DPH, there are pointers. Well, specifically, there's a pointer to the DPB because it has to be there, because CPM states, it dictates that this must be there. Okay, we could put some more stuff down here if we wanted to. But every time you expand one of these macros for a new drive, I did not want to have extra addresses. I mean, these would be all the same. Every time there'd be, another whatever this, 6 more bytes wasted every time we do this. And while you might not care about 6 bytes on a system where you got 128 gigs, we don't have 128 gigs. Everything matters. And at some point, we're going to have to go back through the BIOS and really talk about, things that only get used once. And why don't we get rid of them when we're done? And how do we organize this around? And we'll make a pass through that and clean up all the wasted space in there. And by that, I'm referring to like the cold boot entry point. All the code in there is never called a second time. So why don't we allow ourselves to overwrite it? Like, for example, that code could be reused, or the memory for that code could be reused later on as the BIOS extra stack space, for example. And even the little login messages, like when you boot up, this only gets printed out. Well, this is actually gets reprinted by the warm boot now that I think about it. But did I print anything once and only once during the hard boot? No, I don't believe I do. I think this actually does get printed out each time. Let me hit Control-C and do a warm boot. No, it does not. So this is actually, and I knew there was something that was printed out during the cold boot. So, for example, this memory is all wasted too. Well, I hold all that text in there forever when we don't need to. All right, so that sort of thing. So we don't want to waste a lot of memory is my point. So we have a DPH that points to the DPB because it has to, because CPM says it must. We have a per disk configuration that can't be shared across all the drives because each one has a different starting offset. So I put those in here. The cardinality, right? One-to-one relationship between the starting address and a specific disk. And each disk must have its own DPH. I mean, that's what CPM says, so I stuck it in there, all right? And each disk has to have its own ALV. So these are all tied together to those macros, all right? Or to this macro and those expansions of the macro, okay? Down here, this is shared for every disk that uses the same driver. They're all using the same format. They all have the same write, their same read, and their same init function. Now, I could have put these down here, and maybe I should have. I don't know. But I put them up here on top. And the way this works is, when I have the address for the DPB from the DPH, I have the address of this first label right here. I know where this value is, okay? And if I go and subtract values from this label, I can find these things up here. Just like if I wanted to, I can add values to the address that represented by that label, and I find the values down there. So it turns out that you can, with one label, kind of have two different objects. There's this stuff up here with negative offsets, and there's this stuff down here with positive offsets. So I decided to use this particular style of representing, a super object, right? So here's the stuff that's supposed to be there from CPM, and here's some extra stuff up here. So you can see I put the addresses of these three functions, which are up here in the file. And those functions we've seen before, and we've walked through at great length in their original design. There's been some updates. We'll talk about that briefly here. There's the read routine. This right here is the new code that we added to support multiple disks. Trevor came up with this first draft, and then the two of us kind of figured it out and got it all integrated in here. So in order for this to work, as you may recall, the no cache version of the driver has a buffer to hold an SD block that has to hold the 512 bytes because you cannot transfer less than 512 to an SD card. But the CPM BDOS only wants to work in 128s. So there was some logic down here that had to deal with, well, I have a 512 byte buffer, but that has 4 sectors in it. Which one of the 4 sectors do I want? And is it in the buffer, not in the buffer? So down here, there's some logic. I walked through this before that tries to figure out if the sector that the BDOS is asking for is in our buffer or not. Because every time it reads in a an SD card block, odds are the BDOS is just going to read more sectors that immediately follow it anyway. And we saw that. I had a whole video where we watched what happened when it read the directory and all this other fun stuff. And yes, they kind of read them in order. And this logic down here has to do with, did I already read it in? It's a tiny cache kind of a thing, right? But it's really just a buffer. Now, because we only used to have one single drive, what this code down here is based on is asking whether the track number on the one and only one drive matches the one that's in the buffer. If so, then we know our sector's in there. If it doesn't, then we know it's not, and we're supposed to reread it, okay? That's the original code. The code up here takes it one step further. It has to ask, is the buffer come from the same drive? Okay, so is it got the same disk? And does it have the same track? If so, we can reuse the buffer that's there now. So we had to add the code that checked to see if they had the same disk in addition to the track, all right? And the way we do that is a lot like we used to do this, right? We used to remember there was like a valid flag. That's what this is doing. And then it asks, we have a variable that holds the track number that was last put into that buffer down here, okay? So what we did is we added another variable where we store the DPH pointer that represents the disk whose track is in the SD card buffer, okay? So we have to check the 16-bit value. It's a 2-byte value, right? And if that matches, then we're good. Otherwise, it's not good. And that down here is if it doesn't match, we're going to have to go reread it anyway. Just like this down here, if it doesn't match the same track, we got to go back and read it anyway, okay? So this logic here was added for the read routine, and it was added for the write routine. You notice the write had this same exact lead in at the beginning. This is the major difference right here. The other thing that happened was down inside here, this is where, we store. Here's the last track that we accessed. We stored it in there. This is old news. The new news is we have to also support the DPH value, just like we did with the track, okay? Now, rather than just, this is where there used to be a comment that said, this only works if you started at 800 in hex. We replaced that 2 lines of code with this call to a subroutine. The original one had it hard-coded to 800, only supported one single disk, and then we'd add the track number to that 800 in hex value that was right in this code right here. We remove that code, replace it with this call routine here. Same logic you'll find in the write routine below. I won't go over it now. We'll go to the calc routine that we're going to look at here. And then what that does is this right here. What this is going to do is it's going to calculate, as the doc says, calculate the address of the SD block, given the CPM track number and HL, and the fact that currently selected drives DPH is known to be in the disk DPH pointer variable. So, if we know where the DPH is, let me scroll down for quick review, and we know that the DPH includes this giant 32-bit value. Okay, this is equivalent to when we had it hard-coded to 800 in the early days, right? Early days being last month. This one has the actual address for the drive the DPH represents. So what we're going to do is we're going to load the index register IX with the DPH address, for the currently selected drive. That's what's in this variable here, right? And then what we're going to do is go to 16 and 17 off of IX. We're reaching in on an offset to go grab the 32-bit value out of the DPH. Okay, that's where we're going to go and read the low half and then the high half, and we're going to do the addition 16 bits at a time because we can't do 32-bit additions. So what we're going to do is we're going to add 16 bits together here, and this instruction will set the carry, and that's the key, if this addition results in a carry. So this is the least significant 16 bits are added in this add operation. We save that because we need to get it back later, because we have to use the HL register in order to do an add, because the Z80 doesn't have ways to add other registers and stuff like that. So we need to save the low 16 bits. And then we got to go get the offset, which we know is 0 in this particular configuration, because when I expanded those macros, all the images just so happen to be less than the size needed for 16-bit numbers. But we got to do a 32-bit add so we can deal with the whole drive here and support anything in the future, right? So we have to go get the other 16 bits. And we know that CPM will never have more than a 16-bit track number. So what we're really doing is we're going to go get the most significant 16-bit value out of the DPH, and we're going to add 0 to whatever that most significant 16 bits are. And then we're going to add with a carry the 0 that's in the DE register to the HL register. And if the carry flag was set to 1, as a result of the add up here, because none of these other instructions change the carry bit, we'll take care of the carry in the operation in order to do a 32-bit add. And when we're done with that, we take the HL register and we copy it into the DE register, and then we go get the HL back out of the stack that we save up here, and we return a 32-bit value. In the DE register holds the most significant 32 bits. The HL register holds I said that wrong. The DE register contains the most significant 16 bits, and the HL contains the least significant 16 bits. And if we do a search on this to go back to what we were just looking at, where it gets called, we fall into the code that was always there before, because the code that was there before originally put 0 into the DE register and pushed it, followed by the track number plus 800 in the HL register, which now contains the correctly calculated 32-bit value from whatever offset was stored in the DPH when the macro was put in the call gate file. All right? So we've had a very small impact to the code, but a very large impact to the organization of the code, because he had to reorganize where everything is. So while the retro BIOS allowed you to pound include, either the DM cache, the no cache, or a stub. Yeah, that was true. But now the call gate allows you to include not only just which one you want, it allows you to include which ones you want. You can have a no cache and a DM cache and a stub, and someday when I get it working, an NHCP disk mounted. Okay, so, and if you want a real floppy, we'll write a real floppy driver and put that in here too. So we can have, drive A, which is my, logical drive 0 or whatever, can come from an SD card. Your drive B could come from, a network mounted disk. This one could come from, you could even use a stub in there if you wanted, but it's not too useful in production deployments. And maybe drive D could come from an actual floppy. And all this can be configured by just tweaking this one single file and or adjusting this table down here. Okay? So now if you want to play around, somebody asked, can I work on an associative cache? I got some ideas. I want to work on it. Knock yourself out. Start with this, or the stub, or this one's actually not even ready to go. This is just a big mess right now. It's like a first draft. But all these will have the, the read and the write and the init routines and stuff like that in there as examples that you can start with if you want to get into that sort of thing. All right? Now, this is, as I mentioned before, on a branch that I originally created solely so that I could work on ACP, which is something that some people are working on. Let me see if I can find the doc for it here. There's a spec that's kind of in progress here that has been discussed on the Discord. Somebody working on something called FigForth wanted to implement it and run it on the Naboo, and they decided they want to use a different kind of disk sharing, I don't know, protocol or whatever. So they created kind of a superset of the Naboo serial network link that could support some other features. And I got talking to these guys. I also got talking to DJ about what he was doing with some of his games in the libraries that he's playing around with. So it's unclear to me what's going to happen with what. But this thing here has a specification, and it's not really yet cast in stone. So as things come up and we want something added or whatever, it was easy enough to just add on and throw in here. So by just random happenstance, I ended up looking at and considering how this thing works. And this is what I want to do for my first draft. We can implement other ones as well. It doesn't matter because the code now, all we need to do is hit another driver to the call gate and we've got it. So my point is what I wanted to do on the branch that I'm working on right now was add the ability to access disk images over a serial link. And inside here, you see these storage get and storage put, and there's these get time and close and some error reporting and stuff like that. I'm working on a serial protocol that allows us to use this serial link. It's actually easier and mildly embarrassing that I didn't think about this a year ago. All right. It is easier. I think it's going to be easier than it was to talk to the actual SD card, is my point. I'm like, why didn't I do this on day one? No, to answer my own question, why did I do that? It's because I wanted the Retro to actually represent the embodiment in the features of the original CP/M machines from 1978, and they all had one, maybe two serial ports, a parallel printer port, and some form of one or more disks. And that's what we got in the Retro. That's exactly what we have, and very little more. Okay. But I added the VDP. It became cumbersome to work in that environment, mostly because I did not have multiple disk images like we do now. And I'm trying to cross-develop on a Unix platform and deploy on the Retro. We could have also just done self-hosted development on the Retro if we wanted to, and I know some people are excited about that. We'll probably get there soon enough. The only reason I haven't done it yet is because, I mean, honestly, there's not a good editor. I mean, we could use Ed. I grew up with Ed. I mean, I spent whatever it is, 8, 9, maybe a decade using Ed on CP/M. I am very well learned in using Ed, but it is so incredibly primitive. Other than a demonstration, I don't want to live there. Okay. So there are other ways to do it. I'm excited because somebody posted a note that said that they wanted to work on porting an editor to CP/M. So maybe there's going to be a better editor that we can use that'll actually be a WYSIWYG like look, I like Vi. All right. If you can, even if all we end up with is something akin to Notepad where you can use the arrow keys or something, that'll be fine. Especially if it draws what you're editing on the screen. Ed doesn't really work that way. Someday I'll show you how I use it, and I do kind of use it that way, but it is not an efficient way to edit files by any means. So, again, somewhere down the road, maybe we'll do a demo of that thing. But what am I getting at with all this, okay? I don't want to do self-hosted development until I got a better editor. Somebody's working on one. I suppose I could use WordStar in text mode. But you know what? WordStar, I think, is not exactly free. And I wouldn't even know how to buy a license. I think there's a company still, that owns it. I don't know what the state of it is. So it's not like I can give it away. I happen to know there's copies all over the internet, so you could use it, but I'm sure not going to try and give it away. I don't want to deal with getting takedowns and all that other fun stuff. So it's off until I find out otherwise. It's off limits. So I'm cross-developing. If I'm cross-developing, do I want to send the SD card back and forth all the time? No. What I want to do is type make like this without making a typo. Make more like this, and then reach over and reboot my my retro board. Okay, and that can be made to work if we have network-based access to the file system on my desktop. And with NHCP, that's an option. Okay? And not only is it an option, I think it'll run just as fast as the current SD card driver does right now. So this will make the cross development and reboot cycle go much more efficiently. It will allow people like Trevor, who wanted to do multi-disk support and tinker around with some of the drivers and stuff, gives him a way to do this without disrupting someone else that might want to work on the retro, or another person that wants to create a new caching mechanism and stuff like that. So this is all part of the, how do I break this into smaller pieces so that all of us that want to try and contribute, or at least get one part or another, or reconfigure the retro software, so you can do that. If I made one big monolith, it might be easier to understand, but it would be a nightmare to reconfigure and collaborate and contribute and share. All right? So let's call this part 2 of the giant GitHub reorganization walkthrough, because that's really what's kind of going on here. And this is kind of why I did all this. If we break this up, it's a little more work to understand what's going on. However, it gives us an enormous amount of flexibility, and it will allow many more people to contribute to the project. All right? So let me know what you think. So glancing up, I can see this just passed my 1-hour clock limit on one of my videos here. So I'm going to leave it at this point. Let me know what you think. If you want to look at this thing, I'm really open to any suggestions. You can walk through the fancy init routine and the read and write logic and the new pointers and all that fun stuff and unravel it. Again, to find it, if you go to the CPM software, you got to go to this branch down here, because I don't even know if I want to release it yet. It's still in development. And if you go to this branch, you're going to see the live version of what I'm working on right now. If you want to see the version that matches this exact video, go down here, and this is always the case. These numbers and dates in here, these match the videos that down in this corner down here. The beginning and the end of the video, you'll see a date and timestamp like this. That tag, wherever it is in that list, is exactly the code that you want to look at. Okay? So this matches the state of this video. Down the road, there will be other things going on. So, again, in closing, thank you, everybody, for all your support, all your contributions, all your comments, and every bit of help that you've had on that you've given on this project. I'm really appreciative. Thanks a lot for watching, and let me know what you think in the comments below. I'll see you next time.